Welcome to section 16.4. In this section, we're going to be looking at some additional properties and theorems that allow us to solve line integrals in ways that we couldn't before. So the major theorem we're going to talk about in this section, of course, is Green's theorem, the name of the section. In order to utilize Green's theorem, we have to talk just briefly about the concept of orientation of a curve. So we consider positive orientation of a simple closed curve to be counterclockwise. Okay, so positive orientation is counterclockwise. Another way of thinking about this, especially when you have kind of more complex curves, the region D that is being bounded by the simple closed curve should always be on the left of the curve. So you can see I've got a couple examples down here. So two similar regions. The one on the left over here, see the values are going counterclockwise like this. Okay? Or if you think about it this way, the arrow is pointing that way on the left side of the arrow. That's right over here. So that's where the region D is. So this one has positive orientation, whereas the one on the right here, this is going clockwise. Okay, and the region D, when you look at the arrows, the region is on the right-hand side of those. So that one would have negative orientation. So we bring up the orientation because Green's theorem does depend upon positive orientation. So let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then the integral over C, so the line integral over C of P dx plus Q dy is equal to the double integral over D of the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y, dA. So what this is doing is it is drawing up a relationship between the curve around the region and the region itself. Okay, so we have a relationship now between the curve C and the region D that is bounded by it. And now this tool allows us to solve line integrals using double integrals, okay, in some circumstances, right? Whenever Green's theorem is applicable. But this is now a valuable tool because we've spent an entire chapter talking about how to solve double integrals. So this gives us more to work with. Quick note before we go on to an example. If you ever see this notation here, this little kind of circle around the middle of the integral symbol, this indicates positive orientation when calculating the integral. So if we are given a problem with an integral, a line integral that has this circle on it, all that's telling us is that we may assume positive orientation for that particular curve. And that's not something we need to find or verify or show or anything like that. So let's take a look at our first example here. Evaluate this line integral where C is the triangular curve consisting of the line segments from 0, 0 to 1, 0, 1, 0 to 0, 1, and from 0, 1 to 0, 0. So I've got the shape right over here. Okay, so in terms of the orientation of this, which I'll go ahead, I can mention the note right now. We could solve this line integral normally like we did in the previous sections, but we would have to set up and solve three separate integrals. So, right, because you've got three different pieces, so you would have to set up a line integral for this one for this one, and one for this one, and do them all separately and then add the results together. Green's theorem is going to help us immensely here. We don't have to do that anymore in cases like this. So it said that we're going from 0, 0 to 1, 0. So we're going that way. 1, 0 to 0, 1. So we're going that way. and then 0, 1 back to 0, 0. Okay, and this is, of course, the region D is in the middle here. It's everything in there. So our orientation is going counterclockwise, right? Everything is going where the region is on the left of the curve at any given point. So we do have positive orientation. Okay, so we do have positive orientation in this case. So to set up using Green's theorem, we're going to need P and Q so that we can get these partial derivatives. So in this problem, we have that's P and that's Q. Right, so P of xy is x to the fourth. Q of xy is x times y. And then we need the corresponding partials. So partial P with respect to y is nothing. Partial Q with respect to x is y. So to evaluate, line integral over c of x to the fourth dx plus xy dy. This becomes the double integral over d of partial q respect to x minus partial p respect to y. So just y dA. And now we just need to set up the double integral for this region D. Okay. And this one, we can set it up vertically or horizontally. It really doesn't make a difference. Everything's linear here. But we have, right, this is y equals 0. This is x equals 0. This line right here would be y equals negative x plus 1, right? It's got a y-intercept at 1 and a slope of negative 1. So if we go ahead and set this up, I'll set it up vertically. So we'll do dy dx. Y is going to go from 0 up to the line. So that's negative x plus 1. And then x goes from 0 to 1. Kind of sets the edges there. Okay. And then this double integral is something that we can calculate from the previous chapter. So I'll leave that as an exercise. So this ends up giving us 1/6. So we were able to find the value of the line integral simply by evaluating the double integral over the region that the curve is bounding. Let's take a look at the next example. This one is a great example of why Green's theorem can be so useful to us. So for this one, we're evaluating the positively oriented line integral over c of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy, where our curve c is the circle of radius 3 centered at the origin. So we can assume positive orientation, so we know we're going around counterclockwise. In terms of the evaluation of the integral, so this is P, this is Q. So we're going to get the double integral over D of partial derivative of Q with respect to X, which is going to be 7 and nothing. So 7 minus partial P with respect to Y, which is 3 and nothing, right? So 7 minus 3 dA. And immediately we see that the solution to this double integral, no matter how complicated the bounds are, which they're not very complicated, but even if they were, I'm already much, much happier about solving the double integral of 4 than I am solving an integral with the e to the sine x and a square root of a y to the 4th plus 1 term. So this is already very, very good. Let's see, over dA. Now, when it comes to evaluating the double integral, the new stuff is done, right? The Green's theorem part got us from here to here. Now that we get to this point, this is all double integral work. So we're integrating over a circular disk here. So we're going to go ahead and convert this to polar. So we're going to get double integral of 4 r dr d theta, with r going from 0 to 3. That's our outer radius. And theta, we're going all the way around the circle. So that's 0 to 2 pi. And again, leave that as an exercise, but we can make quick work of this one. And we end up getting 36 pi as the value of that line integral, which in the setup of the problem looks absolutely horrible. But with one simple application of Green's theorem, becomes a very manageable, I would even dare say simple, double integral with just a quick conversion to polar coordinates. So Green's theorem is particularly useful to us in turning more complicated line integrals into simpler double integrals. So note in these examples, the double integral was easier to calculate than the line integral. Now, it will not always be the case that the double integral is simpler. Sometimes we can be presented with complicated double integrals, and maybe we actually can rewrite them using Green's theorem as a simpler line integral and use those to solve some problems. We're going to look at one such use of line integral formulas. So sometimes it is easier to evaluate the line integral, so we use the reverse direction of Green's theorem. One application is in computing areas. Since the area of D can be found using a double integral of 1, that's something we've shown in the past, we want to choose P and Q so that this object inside of Green's theorem becomes a 1. Okay, so basically we want to choose P and Q from the line integral so that if we applied Green's theorem, that subtraction of partial derivatives would become a 1 to give us this. Okay, so if we can pick P and Q to make that happen, that means the line integral will also give us area, just like the double would. So we have some possibilities here. So if we take P to be 0, and then take Q to be x. If we did it this way, we would get partial of this with respect to x is 1, and then partial of that is 0. We get 1 minus 0 is 1. So this is a valid selection that, again, if we used Green's theorem with a line integral with these inputs, the double integral would give us area, which means that this line integral with these components would also give us area. So do the same thing. So if P is negative y and Q is 0, that would give us 0 minus negative 1. So that's, again, just 1. And then we can also have one where we split the difference. If P is negative 1/2 y and Q is 1/2 x, that gives us 1/2 minus negative 1/2, which add up to 1. So the line integrals that correspond to these different cases here, all three of these, are as follows. So we have positively oriented line integral over C of, so for the first one, we have 0 dx plus x dy. So that's just x dy. For this one, we have negative y dx plus 0 dy. So let me pull the negative out in front. That's negative line integral of y dx. And then for this third case, we have negative 1/2 y dx plus 1/2 x dy. So we'll pull the 1/2 out. So 1/2 line integral of negative y dx plus x dy. So what this is saying is each of these line integrals that we have found here, if we were to use Green's theorem, we would get out the double integral of 1, which gives us area of a region. So if they're equivalent, then that means that these line integrals will also give us the area of a region. Okay? And so we could now use these line integrals, any one of them, instead of using the double integral if it suited our needs. So let's take a look at what this actually would look like to find the area enclosed by an ellipse. So first things first, we would need to parameterize the ellipse. So we'll get the parameterization of the ellipse. So we're going to have x. So we have a and b are the two kind of radius values here. So x is a cosine of t. Y is b sine of t. And t is going to go from 0 to 2 pi. So these are parametric equations for the ellipse. Okay. And again, if we're trying to find the area, we could set up using a double integral, but I'm going to show how we do it with a line integral. We could use any of these formulas. I'm going to use this one, the third one here. So area will be 1/2 positively oriented line integral over c of negative y dx plus x dy. So let's see what we get here. So we have 1/2 integral from 0 to 2 pi, negative y, so that's negative b sine of t, dx. So let me color coordinate here. So dx is going to be negative a sine of t dt. And then similarly, dy is going to be b times cosine of t dt. So that's negative y dx, so negative a sine of t dt, plus x dy, so that's going to be a cosine of t times b cosine of t dt. So we've got the 1/2 out front, 0 to 2 pi. This is going to be ab sine squared of t plus ab cosine squared of t dt. Sine squared plus cosine squared is 1. So we get 1/2 integral 0 to 2 pi of just ab dt. So a and b are constants. So it's really like just, you can pull the ab out and just take the integral of 1. So it ends up giving us a 2 pi, which then the 2's cancel. So we're left with just pi times a times b. Right. So, and if you think about it, the ellipse is just kind of like an elongated circle, right, where the radius values are not the same. The area of a circle is pi r squared, right? If you think of a and b as the two separate radius values, this really is like pi r squared, but with a and b together. So this is the geometric formula for area of an ellipse, found using a line integral. So found using one of our Calc 3 techniques of solution. Right. Another type of region that we can work with using Green's theorem are regions with holes. So if we consider a region D that has a hole in it, so we have the curve C1 is the outer bound of D, but then C2 forms an inner bound on D as well. We need to look at how we can handle this. So for D to be on the left, right, which we need for positive orientation is counterclockwise for C1, so that's normal. But for C2, if we also went counterclockwise like that, the region would actually be on the right-hand side because this curve is enclosed within D. So it's actually clockwise for C2. So we're going to divide D into two separate regions. So you can see over here on the right, I've basically drawn two lines that connect the curves together, and I've split the region in two pieces. I've got D prime, I guess, right, or D, yeah, just D prime, and then D double prime down here. That's the notation that the text uses instead of D1 and D2. So you can see here that if we want to apply Green's theorem to this, so we get double integral over D partial q respect to x minus partial p respect to y dA. That's going to get split. Instead of being over the entire region D, we're splitting it over D prime and D double prime. So that's going to be double integral over D prime of that same integrand plus the double integral over D double prime. Okay. And then we can apply Green's theorem to turn the double integrals into line integrals. So instead of D prime, we're actually going to evaluate the line integral over this piece of the curve that goes around D prime. So you can see I have it kind of highlighted in green here going around. So the notation they use for this is actually the partial symbol, like with partial derivatives, because they want the part of the curve that goes around D prime. So this is going to be the integral over the part of D prime of p dx plus q dy, and then plus the integral over the part of D double prime, that's like the purple section down here, of p dx plus q dy. So if we're evaluating these line integrals, this line integral goes around D prime, so the green part. This line integral goes around D double prime, that's the purple. Okay, everything is positively oriented for both. But notice, I can get this all on the page here, since the line integrals along the common boundary lines, so here and here, notice that they are going in opposite directions. And when you take the value of a line integral and you flip it, right, you get the opposite orientation, you go backwards instead of forwards, you end up getting the opposite value, right? If I do a line integral from here to here, from A to B, that will give me exactly the opposite value as if I did it from B to A in the other direction. So these two segments, these little line pieces that I added to the region, they actually cancel. Okay. Because that can be a problem if I just start drawing random lines into this region, then I've changed what the curve is. But the nice thing is, because the orientation works this way on both, they will actually cancel their values out. So it's basically as if they're not there. Okay. And you have the one curve on the outside, the one curve on the inside, right, with counterclockwise versus clockwise orientation. So we end up getting the double integral over d partial q respect to x minus partial p respect to y dA. So that double integral from back here, it became the two doubles, which then became the two line integrals. And now those line integrals are not over the parts of d prime and d double prime. So it's not the green and the purple anymore. Now that these pieces are gone, it's just C1 and C2, the parts that we had before, right? C1 and C2. So we get line integral over C1 of p dx plus q dy plus line integral over C2 of p dx plus q dy. And if you consider C1 and C2 to both be, pieces of the same general, like piecewise curve, this would give us line integral over C of p dx plus q dy. And that, from here to here, that's just Green's theorem for the region D. So we can apply Green's theorem to regions with holes in the middle, and we don't have to worry about, even though the hole in the middle might have opposite orientation around its boundary curve, and there's no connecting pieces, it turns out we don't need them. Green's theorem will still work. So it's a pretty versatile theorem, and that helps us draw a connection directly between the solving of line integrals and the solving of double integrals. But that brings us to the end of this section in our discussion on Green's theorem. So I will talk with you all about more techniques and properties involving line integrals when we come back in the next section.